Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the first tutorial for this week. As you know, this homework is a takeoff on what we discussed in the first module for this week, which is we are trying to get this feeling for how to use the NEGF equations for problems involving spin. And the basic idea is that when you include spin, it's like, let's say we had these matrices, H's and sigmas, which were 4 by 4. Now that we have spin, each point becomes like 2 points, an up and a down. And so it becomes 8 by 8. But otherwise, the equations all stay the same. So what we are trying to do is get a feeling for how to write down these matrices. And we started with the simplest problem. Simplest problem meaning one with, let's say, just 2 levels. So that if you actually wrote down the Hamiltonian, this H matrix, it would look like epsilon, epsilon, 0, 0. And then we went through, wrote the other matrices, the sigmas and gammas, and we multiply it all out to get this trace, this quantity that you call the transmission that we have been calculating in the past couple of weeks. And this is what we calculated. And in this case, because everything is diagonal, the answer is cleanly separated into a up component and a down component. So in a way, you need not have used the matrix formalism. You could have said, well, let's just calculate conductance of up, conductance of down, and add it up. Kind of like what we had done back in part 1. And the answer at the end of the day looks like that. Okay. So this is then what you could call the conductance function, and it depends on the energy. Now, as we discussed earlier in part 1 again, that when you actually calculate the current or the conductance, it depends on the value of this quantity around the Fermi energy. So what you do is, we use that linear response, this Taylor series expansion for F1 minus F2, and we wrote it as QV times minus del F0 del E. And this is in like the first 5 lectures of the notes, if you want to look it up. This is what we did in part 1. And so the conductance, that is, if you look at current divided by voltage, it depends on the average value of this quantity over this window defined by the thermal broadening function. So if you looked at what we calculated for this trace, it has this E minus epsilon square in the denominator. And so it is peaked right around E equals epsilon, because when E equals epsilon, this is 0. That's when the denominator is a minimum. And so the overall thing is big. As you get away from epsilon, this gets bigger and bigger, and that's how it drops off. So if you were to plot that quantity, it would have looked something like this. It would be peaked right around epsilon, and then it would go down. Okay. And let's say we have your chemical potential somewhere down here, way below that, and your temperature is such that if you looked at the thermal broadening function, that is the broadening of the Fermi function, it looks something like this. Okay. What that means is when I'm doing this integral, basically I'm just looking down here. So what matters is simply what this conductance looks like around the chemical potential, around E equals mu. Around that energy. That's all. That's what really matters, right around there. And when you integrate, around there we could almost assume this function is about constant out here, and that would be the value we'd use for the conductance. So we can look at this quantity at an energy where the energy is equal to this chemical potential, somewhere down here. And if this is big enough compared to these gammas, then actually you could drop these. And then you have a fairly simple expression where it says that the conductance is proportional to, there's like 2 terms. One of them is like gamma 1 up, gamma 2 up, and the other is like gamma 1 down, gamma 2 down. Now the question is, you could say, well, if that's the case, can we understand from this why parallel magnets give you less resistance or more conductance compared to anti-parallel magnets. And the way I would argue then is that, well, if you had parallel magnets, let's go there. Remember, when we are, so you have these two magnets that are parallel. So when I'm writing the gamma for this magnet, you know, we had earlier said it would look like gamma 1 up, gamma 1 down, 0, 0. And if you had a spin that was along the magnet, it would be able to get out easily. So that would be big. The other one would be small. So I could write here gamma 1 up as, say, alpha, and the gamma 1 down as beta, with the understanding that alpha is greater than beta. And the same thing, because they're parallel contacts, so I could write the same here also, which is gamma 2 up and gamma 2 down. And here also I could say, well, that's alpha and that's like beta. On the other hand, when it's anti-parallel, that's when I'd say, okay, let's say this is still the same. This has turned around. So now this has become beta and that has become alpha. So in order to understand, extract the conductance of, say, the parallel configuration, what I'd do is I'd say, okay, gamma 1 up and gamma 2 up are both alphas. So it's alpha times alpha. And gamma 1 down and gamma 2 down are both betas. See? So that's how you'd get the G parallel. And if you wanted the G anti-parallel, that's when you'd say, well, one of them is alpha, the other is beta. And for this one, it's reversed. This is beta and that's alpha. And what we need is this magnetoresistance that people define. That's given by the ratio of these minus 1. So the way you usually define it is that magnetoresistance would be like GP divided by GAP minus 1. That's how I think that's how we defined it back in part 1. And that's what's in this lecture 14 of the notes. Now, if you used what we just got, then you'd get alpha square plus beta square divided by 2 alpha beta minus 1, which is equal to, alpha minus beta whole squared divided by 2 alpha beta. Okay. So we just do a little bit of algebra on this to get it into the form we normally have it. So I can take this off. So this you could write as, alpha minus beta whole squared, and I'll put a 2 here, and then divided by 4 alpha beta, and 4 alpha beta is like alpha plus beta whole squared minus alpha minus beta whole squared. Okay. So from here, what I did was just put a 2 here and made that 4 alpha beta, and 4 alpha beta is alpha plus beta square minus alpha minus beta square. And now if you divide through by alpha plus beta square, what you'd get is 2 times alpha minus beta over alpha plus beta whole square divided by 1 minus beta over alpha plus beta whole square. So that's the final result. So this is the magnetoresistance. This is this ratio of parallel to anti-parallel conductance minus 1. And usually this is what you defined as the polarization of the magnet. That is the difference between alpha and beta. That kind of tells you how effective it is. And so this gives you 2p squared over 1 minus p squared, where p is defined as alpha minus beta over alpha plus beta. And this is the standard expression you'd usually see for tunneling type of conductors, this MTJs. As I said, the spin valves, the field started with the GMR devices, where the channel was actually a conductor, where electrons flowed in the conventional way through the channel. Whereas nowadays, what is used a lot is this magnetic tunnel junctions, where this channel is actually a region where electrons tunnel through it. In the sense we are talking about the electrons with this energy, which is way below where we assume the energy level to be. And the reason it can get through is this tunneling sort of. What you're describing is this tunneling process. And in tunneling junctions, that's the expression. Now, what I discussed, again back in the part 1 and also is in this lecture 14 of the notes, is that when you consider spin valves where things are flowing smoothly, not this tunneling type, then usually there is this interesting difference, that is, you don't get this 2. And the basic point is actually something like this, that supposing our mu happens to be, I said that the electrochemical potential is way down here, and so we say the del F0 del E is peaked here, and we only need to look at the value of this down here. But supposing the chemical potential is fairly close to this level, so that this del F0 del E actually is a very broad curve. Something like this. As you know, the width of that function is kT, of the order of kT. So, 25 millivolts at room temperature. So supposing this is close enough to this, that it's kind of all over the place. It's covering this whole thing nicely. In that case, how much conductance you get doesn't depend on the value at this one energy, but rather the total area under that curve. You see? And if you did that, then you'd get a slightly different expression for things. You see, because what would happen then is, I wouldn't just drop this thing like I did before. I wouldn't just drop this thing like before. Instead, I take this and integrate it over all energy. And when you integrate a function like this, you get, okay, what's on top is a constant, but what you can show is that when you integrate something like dE 1 over E square plus gamma square, what you get is something that's basically gamma. I think it's gamma divided by pi. So when I integrate this, what I'll get is gamma 1u, gamma 2u divided by gamma 1u plus gamma 2u. And this will be like gamma 1d plus gamma 2d. And that makes a very interesting difference, you see, because now the conductance you're getting here is almost like the addition of two normal type of conductances. You see, if you had a G1, some G1 here and some G2 here, and in elementary circuit theory, if I asked you to write what is the net conductance, you would have written G1, G2 over G1 plus G2. See? So if you had a simple resistor model with a conductance at the two ends, that's what you'd have got, you see. But what we had for the tunneling resistor was kind of different. The net conductance was like the product of the two things. It was like G1 times G2, that's it. Not this G1, G2 over G1 plus G2, you see. And when you, so this is the form that is more appropriate for the GMR style devices, the ones where the channel is actually a conductor, where electrons, where conduction takes place over this entire range, and so electrons are actually going through these levels at these energies. Whereas the tunneling conduction is, the important conduction is by electrons down here, and their energies actually don't even match your levels. They're way out, and they're kind of just tunneling through it. Now we are talking of electrons whose energies actually match the level, and then go right through it. And then you'd have something like this. And after this, again, you could do the same story. G parallel would be where both are equal to alpha. So it will be sort of like alpha square over 2 alpha plus beta square over 2 beta. Whereas, because up and down are both, alpha alpha or beta beta. And when you look at anti-parallel, it would be like alpha beta over alpha plus beta and 2 times that. And if you take this and then find the magnetoresistance in the usual way, which is parallel conductance over anti-parallel conductance minus 1, at the end of the day, and this was one of the homework problems actually in part 1, where at the end of the day you find the magnetoresistance looks like this, but the factor 2 isn't there. And the main point I wanted to, of course, get across in all of this is how to set up these matrices and think of these so as to use this NEGF formalism. And this is a relatively simple example where you can kind of obtain results that you have seen before in the context of, before we went into the quantum method.